All right. Good evening, everyone. I hope you all are having a wonderful night so far. Before I begin, I'd just like to let you know that now would be a great time to silence your cell phones just before all the speakers begin. So, as a little introduction, my name is Jessica Chen, and I'm the president of the Case Engineers Council, an organization on campus that builds well-rounded engineers and a strong engineering community here at Case Western Reserve University through mentorship, professional development, and of course, community-wide events such as Engineers Week. Now, on behalf of our organization, the Case School of Engineering, as well as the Case Alumni Association, it is my pleasure to welcome you all to the 2017 Engineers Week reception. For those who are not familiar, Engineers Week is an annual tradition at Case Western Reserve. Its purpose is to bring together alumni, students, faculty, and industry members and celebrate the diversity and achievements of our engineering community. This year's theme revolves around 3 key actions that drive the engineering process: ideate, create, innovate. It was selected by members of the Case Engineers Council because it captures how engineering brings what was once imagination into the realities of our world. Just 2 weeks ago, 150 Case Western Reserve students kicked off Engineers Week at the Engineering Challenges Carnival. They were able to give back to the local Cleveland community by teaching close to 700 local kindergarten through 12th grade students and their families about STEM fields through science and engineering activities. Following the carnival, Case Western Reserve students gained career advice from industry members at the Diversity in Engineering Meetup and Sweet Luncheon, were inspired to create and innovate at the ThinkBox Inspiration Tour, and put their engineering knowledge to the test at the Ship Challenge, Jolly Trivia Night, KSL Airplane Competition, and the Weiser Light Bulb Drop. Tonight, however, we are honored to have the opportunity to hear from Dr. Janet El-Kavandi, former astronaut and current director at NASA Glenn Research Center, as she tells us her story on how a student, not unlike many of you out there, can one day reach the stars. Pun intended. But in all seriousness, we are very excited to have you with us here today, Dr. Kavandi, and we thank you for your time with us. At this moment, I'd like to ask the members of the Case Engineers Council to please stand. Come on, stand up. Show yourselves. Awesome. Stay standing, I have some words. No, stay standing, stay standing, stay standing. So, these students are some of the most dedicated, hardworking, and thoughtful people I've ever met. They've been working tirelessly since September to ensure that Engineers Week is a success, and let me tell you, it's not easy. They just make it look that way. You are all superstars, and I'm incredibly proud of everything that you've done and the accomplishments that you've created and the impact that you've made on this community. You should be too. Ladies and gentlemen, please give them another round of applause. You may now be seated. In addition to the Case Engineers Council, this week would not have been possible without other engineering organizations, such as the Society of Women Engineers, Society of Hispanic Engineers, Women in Science and Engineering, Phi Sigma Rho, and the National Society of Black Engineers. We'd also like to send a warm thank you out to the Division of Engineering Leadership and Professional Practice. Your guidance, mentorship, and assistance have been invaluable to the growth of our organization. Another thank you goes out to Corporate Relations and the Case Alumni Association for your generosity, time, and commitment. Engineers Week would not have been possible without you all, and we cannot thank you enough. And lastly, I would like to send a big thank you out to every member of the Case School of Engineering for support in promoting and participating in Engineers Week. Now, without further ado, it is my honor to introduce the Provost and Executive Vice President at Case Western Reserve University, William A. Bud Baslack III.
Thanks, Jessica. Let's have one more round of applause for the CEC and all the work they've done. It's a great crowd tonight, and on behalf of Jeff Dirk, Dean Jeff Dirk, I really wish you a good evening and welcome to this 2017 Engineers Week reception. I know that Jeff was really looking forward to this event. He'd be really pleased to see this great crowd here, but I think as some of you know, a personal situation has taken him out of town for this week. Like me, I hope you've enjoyed the past hour or two of meeting, walking around, talking, looking at the posters, a great set of posters, talking with students. And again, most of those, I think, if not all of them, were from the Department of Mechanical and Aerospace Engineering this meeting. So again, great posters. Congratulations to all the students. Thanks for all your hard work in putting those together. The theme for this week's E-Week is Ideate, Create, and Innovate, which I think really characterizes what the school and the community are about, whether you're in the classroom, the laboratory, and certainly in our world-class facility called ThinkBox. It's all about, again, those three attributes, and we are very pleased to have those, as the lead sort of theme for this particular meeting. I want to begin my comments by thanking, again, those of you who have put this together. I think, as some of you know, I spent my 2 previous positions prior to coming here about 9 years ago now. It's hard to believe. As the dean of 2 engineering schools, and I can tell you, we had E-Week events every year like you have here, but none of them have compared to what you have this year here. The breadth, the activities, the amount of work put into it. Again, so congratulations. And again, that's largely the thanks to the Engineers Council and all the work that you've done. And my notes here says you've done all the work and put in the events this week. So again, great work, folks. I'd also like to thank the Case Alumni Association for their help in coordinating tonight's event, as well as corporate relations and securing sponsors that contribute greatly to the success of this event. We hope you've enjoyed the new format this year and the opportunities for the extra networking we had over the past couple hours. I'd like to acknowledge our event platinum sponsors, Accenture, you can see the list here, and the Case Alumni Association. Gold sponsor Lubrizol, silver sponsor NTI, bronze level sponsors Rockwell Automation, Sherwin-Williams, Nexus Engineering Group, and the Opal Group. The event would also not be possible without the support of our partners across the campus. I think there may be a list here. You can see all the different departments within engineering and across the university. Again, as I mentioned earlier, one department in particular, mechanical and aerospace engineering, led by Dr. Robert Gao, who's right down here, had a record number of student and faculty eager to display their research and innovation. And again, I hope you had the chance. I didn't realize that I walked around looking at many. There's over 35 displays, so great work. Thanks, Robert, for all the great work there. Before I introduce the speaker, I would like to invite all of you to attend the grand sharing ceremony on Wednesday, March 29th at the Maltz Performing Arts Center. 12 of our great faculty members will be honored as we celebrate their appointments to endowed chairs. I think for you students out there, I think as you know, endowed chairs are really the highest level of position a faculty member can achieve at a university, so this is tremendous recognition, so I hope you all can attend. Again, all faculty, staff, and students are encouraged to attend what will be a very special event. Now it's my pleasure to introduce our keynote speaker for the evening, Dr. Janet Kavandi, Director of NASA Glenn Research Center. Dr. Kavandi is responsible for planning, organizing, and directing activities required in accomplishing the missions assigned to the center. Prior to coming to Glenn, Dr. Kavandi worked at NASA Johnson Space Center, where she was the Director of Flight Crew Operations, responsible for the astronaut corps and aircraft operations. She also served as Deputy Director of the Health and Human Performance Directorate, responsible for NASA flight surgeons and human research investigations on the International Space Station. Selected as a NASA astronaut in December 1994, Dr. Kavandi is a veteran of 3 space flights. Dr. Kavandi earned her bachelor's degree in chemistry from Missouri Southern State University, a master's in chemistry from Missouri University of S&T, and a doctorate in analytical chemistry from the University of Washington. Dr. Kavandi is the recipient of the Presidential Rank Award, 2 NASA Outstanding Leadership Medals, 2 Exceptional Service Medals, and 3 NASA Space Flight Medals. Please join me in welcoming Dr. Janet Kavandi.
Okay. Are we on? We're on. Okay. Thank you very much, and I really appreciate the invitation, Dr. Gao, to be here. I think he secured me a while back, several months ago, and it's my honor to be able to speak to you tonight here at this Engineering Week conference and be your keynote speaker. What an honor. I do kind of feel guilty, though, that, as you heard, I'm a scientist, and I'm here at an engineering conference. I almost feel like a little bit of a spy trying to see how engineers work. But, honestly, most of my life, my title has been engineer, and I've been surrounded by engineers my whole life. So I've been that lone, diverse person in that not only being sometimes of a different gender than most of my coworkers, I always was the scientist and gave the scientific thought process that might be sometimes a little bit different than the engineering process. So I think it's been really great. So don't put down your fellow scientists. Those are also very important in getting your work done. So I think we were mentioning what was it like to get to the stars from being this. I was this little kid that grew up in the country. I was born in the state of Missouri. I lived on a farm. What chance in the world did I have of becoming an astronaut someday? So I wasn't. Let's don't quite start it yet because I want to. All right, well, we're starting it. Okay. But, how do you achieve something like that when it's not even within your parameter of achievable goals in life? And so I grew up in this really little country place on a farm, and my dad and I would sit out at night and look at the stars. Because I was in the country, you could see the stars really, really brightly, and you could see all the constellations, and it was a really great environment to grow up, and he was a very encouraging person. And I think the thought process started when he would say, what would it look like if you were up there? And what would we see if we were up there and looking back down at the earth? And maybe it was just that little nudge or a little seed put in someone's brain that makes you start thinking about a possibility that you might not otherwise have thought about. So I remember thinking, well, I would really like to know what it looks like to go up there and look back at our planet and see what the world would be like, or what we could see. I mean, could we see my house? Could we see buildings? Could we see my pet cow? What could we see? So I think my whole life that was kind of in the back of my mind. And then, we had test pilots flying. We had, the challenge to land on the moon in this decade, and we made it. And that was so exciting to me. And then all the discoveries that were made by the probes that NASA was sending out, and then the Hubble Space Telescope and the images we got from that. And I was just so inspired. And I either wanted to be an astrophysicist or an astronomer or something related to NASA. And my ultimate dream would to be actually that person that got to fly in space. So all through college, thinking about, what would it take to get there? What kind of degree would you have to have? What kind of background? What would you have to study? So I kept looking at the biographies of other successful candidates and trying to shape my career and shape my studies so that I could compete with people who had actually made it. And I remember in my dorm when you have those nights where it's the all-nighter and you're doing the finals week and you just are not sure you're going to make it through. And I had put in big block letters about this big above my desk, "Never give up." And I put the image of a person doing a spacewalk, floating out there in space underneath that. And I said, this is why I'm doing this. This is why I'm trying so hard. So I think, just focusing on something, even if it's a huge goal out there, something that you might think is unattainable, it's better to have a goal like that and to point towards something to keep pulling you through day to day, through those really hard days, really makes a difference. And who knows, someday you actually might reach that goal in life. So now, what I'm going to do is start this video, and it will show me at a younger time. And I started in 1995. I was actually selected and showed up in the 15th class of astronauts. And so I'm going to show you my class there. I'm in the upper left up there. What it's like to go through the training process to become an astronaut. I flew all on shuttle. Part of flying in space is being able to fly in aircraft. So all astronauts have to be pilots. So we had to go through all the normal training that any military pilot went through. So we went through survival school. This is parachute landing training. This is dragging your friend around, simulating that he was being dragged by a parachute and had to get himself unattached. The survival training happened both in the water and on land. So these are the flares that we would use out there in the water. And then they took us out on this big flat boat and dropped us into the water as if you were dropping in the water from a parachute. And then they would drag you behind the boat. And again, you had to release yourself from the parachute harness. So all of these things were very foreign to someone who was a chemist or grew up in a laboratory, because I never had done things like this. It was so much fun and so exciting. This is part of the land survival training, so going out and assuming that you had to eject from your airplane, you're in a wilderness, you didn't have a phone or it broke, and how are you going to stay alive for a few days? How would you find water? How would you make a bed? How would you insulate yourself from the cold ground? Make a tent from your parachute? Make a net that you could catch fish with and things like that. Once we passed all of that, we got to fly. And then at NASA, when you learn to fly, you learn to fly supersonic jets. So I had about 25 hours in a Cessna, and I went from a Cessna to an acrobatic supersonic aircraft. This was not an easy transition for me, but it was a lot of fun. And fortunately, I never once got sick in that airplane. This airplane is another challenge. It is the It used to be called the Vomit Comet, and so that might indicate what it was. But you can fly parabolas in this plane, and it would give you an opportunity to see what it was like to feel microgravity. And so it would fly these 20 to 30-second parabolas, and then they would end. So you wanted to not be underneath the biggest guy in your class whenever the end of the parabola happened. And then we got to do spacewalk training, which meant the only place you can really do that is in a big pool at Johnson Space Center. This is part of the shuttle escape system training, where they have a pole that was implemented after Challenger happened that would help you escape the vehicle. And this is the spacewalk training. So this suit that you wear during this training is about a 350-pound suit. So you can't really stand up in it. The only way you can really learn to operate it is under the water, where they can weigh it out until it's neutrally buoyant. Now, the spacesuit's neutrally buoyant, but your body is not inside, nor are the tools that you use. So there is some compensation still. And then we train in the launch and entry suit, which is this orange suit. We train inside simulators, some motion-based simulators that really had all the same displays as the shuttle had. And we had a pilot, and we had the commander. And because no one wants to be a co-pilot in the space shuttle, so we always had a commander and the pilot. And then we had a mission specialist, who's the flight engineer, the mission specialist too, which I got to be in a couple of my flights. We practiced egress training in the shuttle as well on full-scale shuttle mock-ups at a special facility there at Johnson Space Center. And the rappelling was really fun, climbing out the top of the shuttle, doing all these really, really cool, exciting things that you don't normally get to do in your everyday life. So we had a class of 23 people, 4 were internationals. We had a great 2-year training program that got us eligible for our first flight assignment. So my first flight assignment was to go to the Mir space station, which is a Russian space station that is now deorbited. It's in the ocean at this point in time. But I had a great crew. We had one Russian crew member. Charlie Precourt was our commander. He now works at Orbital ATK. And it was a very exciting first mission. We had 2 main objectives. One was to be the last shuttle Mir mission and to bring back the last American on board the Mir. And then the second was to fly the Alpha Magnetic Spectrometer, which is an instrument that's now on the International Space Station on its maiden voyage. And the purpose of that instrument is to measure cosmic particles in space. So I'll talk a little bit about that later. So the space shuttle was an awesome machine. You felt the thrust off the pad. It was such an exhilarating ride. So this is my very first launch. I'm laying there and I'm shaking, and I'm just, the tears are running down my face. I'm not afraid. I'm just can't believe I'm there. I just can't believe how exciting it is to finally achieve your dream in life. So opening the hatch now to the Mir space station, of course, both vehicles are pressurized. You have to carefully approach and dock at the right speed. You're going 17,500 miles an hour. You both are, but you have a relative closure rate. You don't want to close any faster than about 2 feet per second. So this is Dr. Franklin Chang Diaz, and he's a 7-time shuttle flyer and awesome guy. This is the Alpha Magnetic Spectrometer. What it does is it takes particles from cosmic space. It can determine the mass and their charge. So what they're hoping to do is to be able to determine if there are antimatter particles that enter the chamber, because they'll be able to tell that it's the right mass but the opposite charge. So they are anticipating once in 12 to 15 years they might capture one piece. But in addition, they've been learning all this other interesting science and physics about particles that they've been trapping in this vehicle, and now it is on the International Space Station full time. So this is what the shuttle looked like from the Mir. There's a docking system. I mentioned that there's all kinds of equipment that measure the closure rate. It's essentially like a radar gun that you point at your target, and you're able to watch the speed and the rate at which you close. There's a crosshairs that you have to line up just perfectly so that the crosshairs on the shuttle match up with the crosshairs on the Mir space station. Now, this space station had been up there for quite a while. We now fly to the International Space Station, which I'll show you in a minute, on the Russian Soyuz rocket. We don't currently have an American way to get to the International Space Station, so we ride on the Soyuz. But here we are entering the Mir with the Russian crew members, And of course, there's no up and down in space, so everything is okay, right side up, upside down. Sleeping and eating in any orientation is just a blast, and we'll show you about that in a minute as well. Part of the other process of flying in space is carrying up the supplies. You can't really make anything up there. They're just starting to learn how to grow food up there, but you have to bring up water, you have to bring up air, you have to bring up food, supplies, medicines, tools, everything that you need while you're up there, you have to carry up and carry back down. Wearing goggles for nighttime operations, you want to have your eyes pre-adjusted to the darkness. You do go around the Earth every 90 minutes, and so you have 45 minutes in the dark, 45 minutes in the light, and we're getting ready for prox operations, proximity operations, flying around the vehicle, monitoring all the changes that have happened to the vehicle, any micrometeorite impacts that have happened to the vehicle that are significant. The Mir had an impact with one of its Progress vehicles at one point and damaged one of its sections, and we were monitoring the damage there. A lot of the work that Glenn does out here also has to do with flame propagation in space. So flames burn very differently in space. They burn in balls instead of a point at the top, and they spread differently. So there's a lot of experimentation on what types of materials you want to have in space, what types you don't, what kind of off-gassing you have, how fast flames propagate. We're actually getting ready to launch a new experiment called Sapphire here on the next orbital ATK mission. Landing is also really exciting. You've been weightless for a couple of weeks, and so you come back down, you start feeling gravity, and you feel much heavier than you recall that you did when you launched. Your pencil, your book, your body feels tremendously heavy as you come back into the atmosphere. So I was very fortunate that I got turned right around and got assigned to another mission. This is an international mission as well, where we had a Russian crew member the first time. We had a German and a Japanese astronaut on this flight. The European Space Agency and the Japanese Space Agency are partners with us, as well as the Russian Space Agency. The purpose of this flight was to map the Earth in the highest definition it had ever been mapped in three dimensions. This information that we collected is now available to you on your iPhone in Google Maps. So you're welcome, and every time you want, like I used it tonight, whenever I had to get here, this is what saved me, right? That's my Pippi Longstocking look. My daughter wanted me to braid my hair so she could see what I would look like with my hair floating in space, so that was for my 3-year-old at the time. Yeah, so that was one of the coolest things. Now, Google did not pay for that, but there have been many people who have used a product from this mission. It was actually done for the National Geospatial Agency. They won't even tell us how good the data is that we took because it's all classified, but I've been told it's very, very good. So we were able to discover a new island that's out in the Pacific Ocean. We were able to map areas of the Earth that are in dense forested areas, rainforests that have never had people that we know of inside them. So we have a very accurate topographical map of the Earth between 56 degrees north and 56 degrees south, which is about 96% of the population on the planet. So how it worked, we had this big boom that extended out of the payload bay. This is how we got the 3D portion of it, with one receiver out there, one inside the payload bay. We sent the signal to the ground. It bounced back up. It received 2 different locations. As the Earth rotates underneath the shuttle, we would pass over a different swath of land every time that we would pass under the Earth. Earth would pass under us, and then we would have to change these big tapes. That was how we collected the data. Actually, it was the best way to collect the data at the time. So about every 20 to 30 minutes, we would have to change a tape. So we had 24-hour operations. We split into 2 groups, a red team and a blue team, and we had to adjust the altitude of the vehicle above the Earth every day to make sure we were within a few feet of our position at all times, so that map was very accurate. And then recovering this big, long boom at the end of the process. We were trained to do a spacewalk if anything were to go wrong, me and another crew member, and we almost got to do a spacewalk because it didn't quite close there at the very end. It came about within an inch or so, and then it stopped. And so we were getting excited that we would get to go out and do a spacewalk and crank it shut. But of course, it was really just due to the cold, the stiffness of being cold in space. So they pointed us to the sun, everything warmed up, and it closed on its own. So they were happy. Gerhard Thiele and I, my German friend, were not so happy. So we had other ways that the people inside the space station, this is Gerhard, that they are inside the space shuttle, made us feel better. So this is kind of what things that you can do. You can sleep, you float out of your bed. You can exercise on a bike with no seat, because you don't need one. You see you're floating. You can wash your hair in a different way than you've ever washed your hair before. You have to stick the water to your head and soap it up and then absorb it, the soap and the water back out of it 2 or 3 times. This is one way we help console Gerhard by letting him spin there in space before we came home. I got chocolate, so that's one of my favorite things was balls of chocolate. And Mamoru Mori is like the first Japanese to ever fly in space. He is so famous in Japan, and he demonstrated how you can eat a tortilla in space, a very unique way of doing it. Also, symbolically, he put a chrysanthemum inside of a water bubble and a rice cake. And I don't remember what this symbolized at the time, but we had the Japanese flag behind there, but our American pilot snuck up behind him and ate the whole thing. I think it caused diplomatic issues with the Japanese afterwards. He's a Navy fighter pilot, so we had to keep trying. And this is what it's like to dance in space. So we had some music going. Of course, you need no shoes, and so it was really cool. Janice Voss is the other crew member, of great physicist. This is how we got creative in changing about 500 tapes. So you have to shake it up and be a little innovative. I heard innovative earlier today. So we had a great mission. We didn't actually go to another space station on this flight, but we actually brought home one of the most valuable products I think that we've ever had and brought back from space, which was this incredible topographical map. It took them about 5 years to process all the terabytes and terabytes of data, and so now you can, again, use it on your phone. And then my last shuttle flight was a couple of years later. Actually, most of my flights were very close together. We only had 5 people on this mission because the mission was to help build the International Space Station. We did put into space the airlock, which is the chamber on the space station that astronauts use to do spacewalks. So it's the chamber you go into. They pump all the air out of it. The people put their spacesuits on first, of course, pump the air out, and then you were able to go out and do a spacewalk. So this is a night launch. I was a little bit afraid. I was a flight engineer. Afraid I wouldn't be able to read my books at night, but there's no problem because the engines on that thing light up the inside of the shuttle so brightly that you have no problem reading your manual. So lots of vibration and shaking, and awesome. Never gets boring to launch off the pad on a space vehicle. So this shows the rendezvous to a space station. So we backed up to the space station. The commander on this is Mr. Steve Lindsay. He's an Air Force test pilot, and he now works at Sierra Nevada Corporation on the Dream Chaser, which is an option to fly Americans to space, a commercial entity like SpaceX. And this is the airlock that we took to the space station, and you can see it applied there on the right-hand side. This is the size of the astronauts as they climb down the laboratory, which is there on the space station, where most of the experiments that I showed you, the combustion, the fluid experiments, that's where most of that happened. But this vehicle now provides the way that Americans put on the spacesuits, go out and do spacewalks. Every time you do add a section, though, you have to integrate that. You have to put in the piping and the tubing, and so that you get the coolant flow into that new section, the air pressurization into that section. I was able to fly the robotic arm. That was my primary mission in addition to being the flight engineer. So I was flying the individuals around on the end of the arm, and another person was using a different Canadian arm to install not only the module itself, the airlock itself, but also all the air tanks that go around it. So those little doghouse-shaped items are oxygen tanks and nitrogen tanks that we put on the outside that cause the repressurization to occur. Like I said, there's no air up there. You have to bring everything you use up to space. We have learned to recycle water, though, so we don't have to bring water up all the time. We actually learn to recycle urine and sweat and all those cool things so that you actually can make it your coffee the next day. So you back away from the space station, much like you approach it. You do a fly around like I discussed earlier with the Mir space station. You photo document the whole vehicle. This is back when it was a baby space station. Now, of course, it's much larger. The same kind of crosshairs, the same attention to detail. Usually the commander did the fly up and approach and dock, and the pilot did the back away. And there I am, kind of being my flight engineer role there with everybody else. So really interesting opportunity to help create a station that's still up there and should be up there for about another decade. Again, we were doing water experiments because it's just really cool. This is an air bubble inside of a water bubble. So when you have air inside of water, you can see the person in the background is upside down in the water bubble. If you can see him clearly, he's right side up in the air bubble. It's just really cool to see the physics actually at work. Things that you only study about, in laboratories, about the theory of it, you can actually do these experiments when you're actually you're up there in space. And we actually also filmed part of the IMAX movie, the ISS 3D movie. So this is a scene from that movie as well. So we set dinner up and got to play for a little bit up there while we had dinner. This is on the Russian segment. They have a different kind of food system than we do on the American side. They have cans of food. It's kind of like dog food or cat food. You open it up, and it's sticky. They said one thing you'd have to do, if you throw that, just don't hit the camera. And I hit the camera because, when you throw here, you anticipate the arch. You forget about that in space. There's no arcing the ball. Everything is just a straight shot all the time. So the entry back into the atmosphere, you can see the plasma. All the air molecules are tearing apart as you come back through the atmosphere at Mach 26. And then you got to slow down from Mach 26 to about 190 knots for approach and landing, and then touch down about 145 knots there on some fairly small tires compared to that vehicle. The pilots really practice a lot. They only get one shot. You can't go around. There are no engines left, so you do have to plan it right the only chance you get. So we got to walk around the vehicle, and of course you get very tight with your crewmates, and it's just the most amazing experience I can describe to have had the honor to be part of such an incredible team that makes this happen. Not only the crewmates that you fly with, but all the ground support people and everyone at NASA and all the contractors that make this possible. It's just incredible, and I'm just such a lucky person to have been a part of it. So I think at this point, if you're interested, we could take some questions, and then I'll show another little quick finale at the end that will show you where we are today. So this is past history. I'll show you where we are today, if you like. So I have one back here with a white sweater or white jacket on. If you want to stand up, they'll pass you a microphone.
Hi.
Hi.
What would you say are the essential skills that you see for the next generation of astronauts?
The skill set for the next generation of astronauts. Some of the most critical skills that we found were not the ones you might typically suspect. We find, so I was the chair of the selection board the last cycle. There's one going on right now. In the last cycle, I was the chair of the selection board. We had about 6,000 qualified applicants for 8 jobs. So all these people were incredibly smart. They had advanced degrees. They were, well on the top of their grade GPA areas. So it's really hard to choose even just who to interview. We interviewed about 120 people, and all of those were valedictorians of their class. They're all summa cum laude or magna cum laude. They're all these incredible people. But you know what sets them apart, other than that there's a physical too. So a lot of people kind of gets, there are unfortunate things that we inherit in our genes that they don't always make us eligible, certain health issues that you can't accept whenever you're going to Mars or something like that. But one of the most important characteristics is the ability to get along well with others. Because if you're going to go live on a space station for 6 months with somebody and maybe 2 other people in a can, you really have to be easy to get along with. And you have to take things as they come. You have to roll with it. You have to be able to support your fellow crewmates. things are going to break all the time, you know, and you don't always have the tools that you need, and you don't always have a replacement for what you need. So you have to be very ingenious, and you just always have to have a good attitude and a good approach to problems. Because if you get depressed, if you get sad, if you start blaming each other, if you split up into he said, said, or those ground people don't know what they're doing, then it really falls apart quickly. So I think part of the skill set that's most valuable in any job, and especially in something like this, is the ability to work well with others, literally work well with others, like you're taught from kindergarten on up. Play nicely, defer to the other person when it's their turn to speak, listen well, and take input, be open to suggestions, don't take things personally. Those are some skill sets that not every adult makes it to adulthood with. And that's a real critical skill set for a tight team that needs to get something incredible done. If the U.S. and other countries are going to spend a lot of money on your training and count on you to be successful in a mission like this, that's essential to being a successful crew member. Okay, who else might have a question? In the very back, someone's standing up. It looks like a red or dark-haired. There you go.
Now, recently in the past 6 months, I've heard a lot about this R5 or Valkyrie robot. And I'm not sure, I know it's based out of Space Center Houston. I'm not sure if you have, a foot in all the different departments, so to speak. But I was wondering, because to my understanding, you've been using open innovation as a way to further advance the potential and capabilities of NASA's existing potential. So I was wondering if you could speak to the kinds of benefits that you gain from those advancements in open innovation that you usually don't really think about. The way of being able to connect with markets and people that NASA wouldn't usually have a connection with.
Oh, we have someone right here and for this table that you want to talk to, who is part of our innovation and technology office and outreach, and how we take technologies that we've developed at NASA and put them out into the community for applications like the Google Maps on your iPhone. It wasn't actually intended for that purpose to start with, but there's a lot of technologies that we have that we share with the community. And I think your question is more, how do we then go out there and seek out new innovative ideas that NASA probably doesn't already have, and go out and seek those to use within the agency. And I think it's through a lot of the same process. We're very active, and we were just talking earlier tonight with Case Western here on how we can collaborate more with the students. We have Pathways internships that we allow students to come and work on site. That really helps bring innovation and new ideas and new approaches to problem solving than we're used to. So we have, the average age at our center is getting up there in the upper 40s, lower 50s. They're pretty set in their ways. They went to school a really long time ago. So hiring and bringing in fresh blood and with new ideas and new technologies and new approaches to things really, really help a lot. So we really encourage and like to hire young career folks into the center. We like to collaborate with the professors here at the different universities around the country. Depending on where the NASA center is, we tend to collaborate more with the local universities, but we can collaborate with anyone, anywhere. We also work with local industries to both spread the wealth and knowledge out to industries, which sometimes start new companies, but we also take input from companies who have new bright ideas or suggestions to us. We just talked about a concept that we don't actually have the capability for right now. We are working on a new energy storage effort and this is aeronautics side. We have pretty good batteries for space because these lithium batteries are outside, and for the most part, and they won't hurt people if they were to vent or rupture, but they would cause problems, but they wouldn't necessarily hurt people. But if we talk about new batteries for commercial spacecraft, if we're going to do a hybrid electric design, we don't really have an energy storage device for that right now. And we are actually we're going to have a workshop where we're inviting people, industry, universities, anybody with bright ideas on new chemistries or new technologies or new approaches to this effort that we haven't come up with yet. And so that's one way. And you mentioned robots. There's robotics is spawned a huge interest in around the country, around the world, and how to apply robotic technology. The robots, the robotic arms that you saw in those videos are pretty old school now, but from that, we spawned a lot of new work with robotics, and I think all this interchange of ideas is essential to both the way we operate and colleges and universities and industry today. So the partnership is really important. Okay, let's see. The male right here, you have a vest on.
What is the coolest piece of technology or engineering that you came across on your missions up to space?
I think, well, the alpha magnetic spectrometer is probably one of my favorite. I think it was an international collaboration of about 17 different countries, all over the world. And one of the most interesting dinners I've ever had in my life was to go to Italy and to Bologna, and we had this dinner conference with all the world's leading astrophysicists. And it was the most mind-blowing evening of my life because we had all the world's leading astrophysicists arguing about what they might see from this instrument, what kind of data they were going to get. And everyone was proposing their own theories about what particles they would see, how much they would see, what energies they would see, and they were trying to teach some of our fighter pilots astrophysics, which was the most hilarious thing ever. Now, our fighter pilots are really smart. These guys all have at least master's degrees in engineering, but they hadn't studied quantum physics for the most part. And so trying to get these people that, there's one professor there, he looked just like Einstein. He had the hair, he had the mustache. His name was Professor Zikiki, and he was awesome, and he was trying to explain in the simplest way he could some of the basic cosmic physics that he was trying to learn from this experiment. And our commander would say, I think I understand. I think what you're saying is this. And he goes, no. I start over much lower for you. So it was such an interesting evening. It was so much fun. And of course, our commander had such a good sense of humor. It was just a great evening. So that's probably my favorite piece of technology that's still flying and still producing a tremendous amount of data that's being published all the time. And so a short answer is probably it. Otherwise, the mapping mission was also really, really interesting. Okay, right here. Okay, do you need a microphone? Yeah, right here in front.
So you've had a very successful career, obviously, being the head of NASA Glenn. But was there a time in your life where you felt that, I might not be able to progress? And, could you describe that moment and how did you overcome that feeling?
I think that happens to everyone at some point in their career, even multiple times. So we're never sure. We don't have the crystal ball. We wish we could see what's going to happen because it's always very difficult, especially early in our careers, waiting for that first job opportunity and where it will lead us. So I have a son who's just gotten his first job after graduating from college. I have a daughter who's working on her master's degree. They're right in that phase. My son got his first job, so he's like, I've got the first one down, and then we can progress from here. And my daughter is like wondering what she's going to do when she graduates, where's she going to end up. So it's a world of uncertainty at the beginning, and all I can say is it works out, but it doesn't feel like it early on. So that's why, in part, I had that sign above my desk that kept me focused on, never give up. It may not always work out. Not every opportunity is going to pan out. But you will get more opportunities. And, if you want to be very optimistic and look at the silver lining, there were some opportunities that I really wanted out of college that if I had gotten, I wouldn't be standing here today. I wouldn't have gotten the opportunities that I got later on by another opportunity. I ended up working for a battery company as my first job. It was not the job I wanted. It was the last thing I thought I wanted to do, but it led to a connection that led to a Boeing Aerospace job, and that opportunity led to my ability to go to get a PhD, and then that opportunity gave me the PhD thesis, which was a NASA-related thing, and then when I interviewed at NASA, it made me ready to accept this challenge. So had I gotten my first choice of jobs, I wouldn't have had the really exciting career I had. So you might say everything happens for a reason. You might, But just roll with it and know that, you know, there's something out there that you're going to be happy with. There's a job out there that you're going to be really proud that you're part of. And if you're not, there are other opportunities. If it ends up not being your dream job and you want to go out and do something else, you can either always go back to school, or you can, you know, go out and find the next phase of your life in a different location. But, you know, the more, you know, experience that you get and the better you are at what you do, because those references help, those grades really help, then you'll have a lot more opportunities in life. So don't despair. Okay, let's do one more question, then I'll end up with where we are today. Right here in the middle.
All right. Hi. Hello.
Hi.
So I had a question about your specifically your mapping mission that you went on, and I was wondering what technology you use specifically to do the mapping, and if you were tasked with, say, mapping another planet like Venus, what mapping technology would you use?
So these were two different types of radar systems that were used. One was to map, and I was trying to remember which band, X-band and S-band perhaps. I'd have to go back and check for sure. But two different wavelengths, and one mapped the actual hard surface of the planet, and one would actually map the foliage of the planet. So the German Space Agency wanted the topographical with the foliage, and the mapping agency wanted the actual crust of the Earth. So we didn't map over the water unless we knew we were coming up to some islands, and we would turn it on, then turn it back off to save some of the tapes that we use. So it's the two different kinds of radar bouncing off the planet, being received by two different receivers. You can go online. JPL has a whole website about it, and will explain in great detail about the actual instrumentation used. I think the actual instrument is in the Smithsonian right now. At least we sent it there. I think it was hanging up. It might still be there. So really interesting capability, and hopefully you can go online and learn all you want about it. Actually, on that same website, you can tell it anywhere in the world you want to look at with the data from that mapping mission, and it will show you the city or the location from that data. So that's also really interesting. So let me end with where we are today. So NASA today, of course, we retired the space shuttle, which made me sad, but we did need to do that in order to pursue the next phase of exploration, which is to go to Mars or to beyond low Earth orbit. So the International Space Station is in low Earth orbit, about 220 miles above the surface, up to 250 miles. It goes around the planet every 90 minutes, and that's where we have 6 people on the station right now doing experimentation. What we're building is the next rocket that could go to the moon, it can go to Mars, but it can carry humans farther than we've ever taken people before. It's called Orion. The module, the capsule is much bigger than Apollo, but it looks like Apollo. It's Apollo on steroids is what people joke about. And so the rocket is much bigger. It's the Space Launch System rocket. It's built in Huntsville, Alabama. So each of the NASA centers, 10 NASA centers around the country, all have their own role. The NASA Glenn Research Center is building the service module, which is the piece that fits under the crew capsule, and it contains the fuel systems, electronics, and guidance systems that help guide the capsule with the people in it once it separates from the first and second stage rocket. So that's what we're doing. We're testing that out at Glenn. We're doing a lot of the health systems inside that vehicle. And so what this last little 2-minute video, 2.5-minute video shows is kind of the history of where we started and where we are today, and it's going to have its own sound and music, so I'll just let it play.
Roger the pitch. 7, 6, 5, Roger, you're looking good. 3, 2, 1.
We are the explorers. We have a need to find what is out there. It is a drive inside each and every one of us. The drive to wonder, to push the boundaries, and to explore. We expanded across our lands, settling new frontiers. We took to the oceans and learned that we could cross treacherous expanses in the pursuit of discovery. And then we took to the skies and flew. But that wasn't enough. We left the planet and redefined what was possible. We flew in space. We walked in space. What once was a melodramatic flight of fantasy became reality. Then, a new generation of spaceships captured hearts and minds for 3 decades and helped build a castle in the sky that is our lasting home in space. We have always looked up. For centuries, we wondered what was on the other side of the sky, and we have begun to answer that question. We have learned that all the exploration humankind has achieved is only a beginning. Right now, men and women are working on the next steps to go farther than we have ever gone before. New vessels will carry us, and new destinations await us. Everything we have ever accomplished leads to this moment in time, where exploration will now take us to the planets and the stars. Our nearest neighbors in the night sky have beckoned us, invited us, dared us to reach for them. We are the explorers. Throughout our history, we have taken both small steps and giant leaps in that pursuit. Our next destination awaits. We don't know what new discoveries lie ahead, but this is the very reason we must go.
So thank you very much for your attention tonight. I really enjoyed being here. Thanks for laughing at all the right times, and I appreciate your attention tonight. Good night. Thank you. Use the microphone.
So I think I speak on behalf of everybody in this room that was an incredibly inspiring and insightful presentation. So let's give her another one more round of applause. So we really do appreciate you taking the time out of your night to come talk to us tonight. And so on behalf of the Case Engineers Council and the CAA and everyone, we just want to give you a little token of our
Thank you so
thanks.
much. I really appreciate it.
yeah,
And thanks
no
again for
problem.
being such a great audience. All right?
Good evening. My name is Greg Hessler, and I'm here on behalf of the Ohio Alpha Chapter of Tau Beta Pi, the Engineering Honor Society, to present the annual Srinivasa P. Goody Memorial Engineering Teaching Award. Srinivasa Prasad Goody, or Vasu, graduated summa cum laude from the Case School of Engineering with a degree in a bachelor's degree in biomedical engineering. He was an exceptional member of Tau Beta Pi and was also the recipient of the Chairman's Award in biomedical engineering. He accepted admission into the Case School of Engineering with a full tuition scholarship and was to begin his medical education there in the fall of 2004. Unfortunately, Vasu was taken from this world before he was able to fulfill his promise. To commemorate Vasu, Tau Beta Pi has created the Srinivasa P. Goody Memorial Engineering Teaching Award in a partnership with the Case School of Engineering. This award seeks to acknowledge a faculty member who has shown exemplary undergraduate teaching. Each year, Tau Beta Pi members are given an opportunity to nominate their engineering professors. All nominees are then interviewed, and a professor is then selected to receive the award. This is despite how difficult it is to narrow down these incredible nominees. This year we had 7 nominees. The nominees were Dr. Richard Bachman from the Mechanical and Aerospace Engineering Department, Dr. Harold Kanemacher from Electrical Engineering and Computer Science, Dr. Mark DeGeer from Materials Science and Engineering, Dr. Michael Hoare from Macromolecular Science and Engineering, Dr. Hatsuo Ishida from Macromolecular Science and Engineering, Dr. Katie Wheaton from Civil Engineering, and Dr. Gary Wennick from Macromolecular Science and Engineering. The 2017 Srinivasa P. Goody Memorial Engineering Teaching Award will be given to Dr. Harold Kanemacher. Well, let's learn a bit more about why he's so deserving of this award through a video.
I'm Alice Zhang, and I'm an engineering physics major from Shenzhen, China, and I plan on graduating in May 2018. I nominated Professor Kondemaker because I took discrete math with him, and I really liked the class, and it was engaging. It's easily my favorite class at Case so far. I think students relate to him mostly because of the stories he tells in class. Students want to know what to look forward to past graduation, and he really brings his experiences into the classroom.
I'm Harold Kondemaker. I teach the Introduction to Programming in Java. I teach discrete mathematics. I'm teaching a graph theory course, and I teach programming language concepts. I have a lot of stories from industry that I like to tell the students, especially things that they shouldn't do. And a lot of them are kind of funny. I mean, I once caught a computer on fire, and my boss was actually thrilled because he's like, I've seen it in movies. I've never seen a computer actually catch fire. And then the hardware person came along, and the boss was like, what do you think that is? Do you think it's the power supply? And the hardware guy says, no, from the smell of it, it must be the memory chips. My boss said, oh, we don't pay you enough. So tell me, from the smell, were those 32 meg or 64 meg chips melting? When I think about what I went through in industry, it really does kind of guide how I'm teaching them, because I want the students to be as good as possible. You know, I want them to bring in the best things that I saw from industry and kind of avoid the worst things. I mean, a lot of things like making sure you test what you do. Don't just write things at the last minute and turn it in. People in industry were doing that, and then programs were crashing. Everybody remembers the blue screen of death. Well, okay, students today don't remember it, but faculty remember the blue screen of death. That was just natural. Everyone's like, oh, my computer crashed, haha. But it shouldn't be that way. This is because people didn't realize the importance of testing and carefully thinking through code, and now we know. When I graduated, I just sort of assumed everybody out there was just amazing programmers, and it was a shock to me to find out that most people really didn't know what they were doing. I was talking with people who were vice presidents of major technology companies, and they would say things, and I'd be like, didn't your professor at college teach you better? Because mine taught me better. And I started thinking I could have a bigger impact if I start training the next engineers rather than spending my time sort of, you know, they were giving me things like, oh, we don't like the color of this button, you know, change that. And I was finding that I would have a bigger impact rather than writing specific packages to actually be training the next people.
Professor Kondemaker is not afraid to use his mistakes to potentially help his students learn. Him doing it on a whiteboard, you get to follow through that thought process with him, and same thing in Java, if he's live coding, you're following through line by line. It's hard for professors to do live coding because, you know, they have to type and think at the same time and explain what they're doing. So not a lot of professors do it.
I'm not so worried about making mistakes because I don't think my job is to be perfect. I think my job is really to get the students interested in the material, so then they'll go and learn the right way to do it. So if I make a mistake now and then, I don't think it's that critical. Well, when I teach, I don't like to have a strict lesson plan. I like to have more of an outline of what I want to cover. And so then it allows me to be flexible so students can contribute and make suggestions, and so we can do it. So I will be doing the math proof on the board with the students giving me input, or I will be writing a program and the students will be giving me input. And sometimes it goes well and sometimes it goes disastrously, because sometimes I'll get bored of a problem and say, you know what, I'm going to do a different problem, and I'll do it right on the spot without realizing it's impossible. It's part of the teaching thing just to try to keep the class involved, keep the students involved, and not just presenting them with a solution, but showing them how we think about it and how we come up with the solutions.
So Professor Kondemaker is fun to learn from because he really cares about his students, and it's great trying to figure things out with him other than him teaching you something. For example, in discrete, I was kind of working out problems step by step, and I was in his office hours a lot, and he'd coach me, and he'd only give those you're on the right track pointers and not actually tell you where to go from there. And that really helped me.
The students is what gets me excited about coming to CASE. I mean, the students here are amazing. I mean, my first term, I realized K students were different because I was lecturing on the board, and I looked out and there was this one woman, and she was laying back. She had her feet back. She was like sleeping. Her eyes were closed. And I was like, some student who was up late at night sleeping through my lecture. And I'm going ahead talking about something, and suddenly she goes, "Wait a minute, that makes no sense." And I was like, "I thought you were asleep." And you're right, I was wrong. And so here she was. And so that just let me realize that students here are a little different. They catch me in all my mistakes. They really listen to what I say. I mean, my goal is to be a good teacher and then to get feedback from the students that they appreciate what I'm doing. I mean, that's just, it's just, I can't really put into words, honestly. It's just, I mean, this is what I want, is for students to appreciate what I'm doing, to think that they're getting value out of what I'm providing.
Thank you. I just want to thank the students in Tau Beta Pi for this. Like I said, it really means a lot. I'm very touched and honored by this. I know my classes are really hard, but you keep coming back, and it really is just an honor for me, and I'm very lucky to come to work every day with people who are so passionate about learning. It just keeps me inspired all the time. Thank you very much.
Well, it's been a great evening, and I just want to thank everybody for being here on behalf of Jeff Dirk and the school. Thank our guest speaker. Great presentation. There's a lot of envy in this room tonight, I'm sure. Congratulations, Harold, on some great work. Again, thanks everybody for being here. Thanks to the eWeek committee and for all of your hard work. And there is dessert and coffee waiting outside the doors here. So thank you, everybody.